Welcome to the Celestial Stuff, and it's lovely to have you here, and please subscribe to the channel so you don't miss out on any of these videos, and also do tell where you're watching from. So, find a comfortable spot and let's get started. Time, it's the one thing we all live in, yet no one truly understands. We measure it, chase it, waste it, and wish for more of it, but what is it, really? Is it a ticking clock, a flow we're carried along, or just a trick our brains play to make sense of change? From the dance of the planets to the ticking of atomic clocks, from the birth of the universe to its possible end, the story of time is as strange as it is profound, and once you start looking closer, you may never see a single second the same way again. Imagine you could stop the universe, not just the planets, not just the atoms, but everything. Would time itself stop with it? Or would it still march on, silently ticking in the background, even if nothing changed? This is not just a philosophical curiosity. It's a question that has gnawed at some of the greatest thinkers in human history, from Aristotle to Einstein. Time surrounds us, shapes us, and eventually claims us, yet we can't hold it, can't see it, can't even really define it without slipping into paradoxes. It's the stage on which all events occur, yet the stage itself might be an illusion. When you try to pin time down, it escapes between your fingers. Is it a physical thing, like space, with measurable dimensions? Is it a mental construct, a trick of perception invented by our brains to make sense of change? Or is it simply a mathematical tool, a number we attach to events so we can put them in order? The strange truth is, time might be all of these at once, or perhaps none of them at all. Even the smartest minds can't give you a universally agreed-upon definition of time. In physics, time can be treated as a coordinate, like a line along which events are plotted. In philosophy, it becomes a question of existence. Does time exist independently of the events within it, or is it a property that only emerges when something happens? In psychology, time isn't out there in the world at all. It's in here, in our heads, as a deeply subjective experience. The problem is that each of these perspectives works beautifully in its own domain, yet they don't always fit neatly together. Physics describes time as a dimension in space-time, something woven into the very fabric of the universe, inseparable from space itself. But if that's true, what's to stop time from being just another spatial direction we haven't learned to navigate? Yet our experience tells us time feels nothing like space. You can walk east and then walk back west, but you can't walk yesterday and return to today. This tension between our intuition and the mathematics of the universe makes defining time incredibly tricky. Isaac Newton saw it as an absolute, universal river flowing evenly for everyone, everywhere. Albert Einstein shattered that picture, showing that the flow of time depends on your speed and your position in a gravitational field. Quantum physics, in turn, raises the possibility that time may not be fundamental at all, that it might emerge from something deeper, something timeless. But before we can explore those radical ideas, we have to acknowledge a curious fact. We can measure time with astonishing precision, down to billionths of a second, without truly understanding what we're measuring. It's like knowing the exact weight of a ghost without knowing whether the ghost even exists. That's the strange paradox of time. We live by it, yet we do not know it. And perhaps the slipperiest part of defining time is separating the map from the territory, the measurement of time from the essence of time. We've built clocks, calendars, and atomic oscillators. But these are just our tools, our human constructs. They don't reveal whether time is something out there in the universe or something in here in our minds. When a clock ticks, is it marking the passage of a real, flowing entity? Or is it simply ticking through a series of events we've chosen to label with numbers? That question, whether time is an independent reality or a convenient illusion, will shadow everything that follows in this exploration. Because until we know what time is, every discussion about its nature, its flow, and its limits is built on shifting ground. If you try to imagine a universe in which absolutely nothing changes, no planets moving, no atoms vibrating, no light traveling, what does time mean in that context? Would there be any sense in saying that time is passing if nothing at all was happening? This thought experiment strikes at the heart of the idea that time might simply be a way of tracking change. From the moment humans first began to wonder about the world, they've tied the concept of time to motion and transformation. We notice the sun rising and setting, our bodies growing and aging, the leaves turning color in the fall. In every case, time seems inseparable from the fact that something is different now compared to before. Without this before and after contrast, the idea of time feels hollow. Philosophers have long debated this relationship between time and change. The ancient Greek thinker Aristotle argued that time is the number of movement in respect of before and after. In other words, time isn't a thing in itself, it's the measure of motion, the ordering of events. Without motion, without change, there would be nothing to count, and therefore no time to speak of. On the opposite side, some have argued that change happens within time, implying that time is the container or backdrop in which these changes occur. To see the strength of the time as change idea, consider how we actually keep track of it in daily life. We look at clocks, devices whose entire function is to undergo a predictable, repetitive change, whether it's the swinging of a pendulum, the oscillation of a quartz crystal, or the vibration of atoms in an atomic clock. These clocks don't measure some mysterious fluid of time flowing past, they measure regular changes and give us a numerical way to label them. This idea has a profound implication. If somehow, all motion and change in the universe froze, our measurement of time would freeze too. Suppose every particle in existence stopped moving, every energy exchange halted, and every field went perfectly still. There would be no tick of a clock, no heartbeat, no aging, no light traveling from one place to another. Even if we tried to wait in that state, there'd be no difference between one moment and the next, because there wouldn't be a next moment in any meaningful sense. Time, in this view, is just the ordering of change. Remove the change, and the ordering vanishes. Interestingly, physics both supports and challenges this view. In classical mechanics, time is an independent variable. You can write equations that keep time ticking even if all positions and velocities are set to zero. But in more modern approaches, particularly in certain interpretations of quantum gravity, time doesn't appear as a fundamental ingredient at all. Instead, the laws describe relationships between changes, and time emerges from those relationships rather than existing independently. Think of it like a film reel. The reel is made up of still frames, each capturing the universe in a frozen instant. The sensation of motion, and the feeling of time flowing, comes from playing those frames in sequence. If the sequence never changed, if we just stared at a single frame forever, there would be no time for us to experience. The time in the movie is simply the ordering of frames, not something inherent in each frame itself. There's also an interesting tie here to thermodynamics. We often say that time flows forward because things change in one particular direction. Heat spreads from hot to cold, eggs break but don't unbreak, you grow older but never younger. These changes are all processes that increase entropy, or disorder. In that sense, time and change are connected through the very physical laws governing energy and matter. And on the smallest scales, this link between change and time becomes even stranger. In quantum physics, the act of measuring a system changes it, and the possible outcomes can only be predicted in terms of probabilities. Time in quantum mechanics is not a tangible flow, it's the parameter that connects one measurement to another, one change to the next. If there were no events to connect, the concept of time would evaporate into meaninglessness. We can also turn the question around and ask, is all change time? Imagine a universe that consists only of a pendulum swinging back and forth. We could measure the swing to mark seconds, but if we ignored the pendulum, we might think no time had passed. That suggests time is not just change, but our observation and measurement of change. Without a conscious observer to register it, the universe might still change, but the notion of time as we understand it could be nothing more than an abstract idea. This leads to one of the deepest philosophical possibilities. Perhaps time is not an independent entity or a background dimension, but simply the name we give to the ordering of change we experience. If that's true, then the question "what is time?" becomes inseparable from what is change, and what does it mean to experience change? It also means that when we say time passes, we're really just noting that the universe keeps rearranging itself. In a way, this makes time both incredibly concrete and incredibly elusive. Concrete, because change is everywhere and measurable. Elusive, because without change, the very concept of time falls apart. And maybe that's the strange truth we'll have to carry forward. Time is not some invisible river flowing around us, it's the dance of the universe itself, and we are counting its steps. Long before anyone built mechanical clocks, before sundials, before even the simplest calendars, humanity lived under the rule of nature's own timekeepers. The first clocks were not made of gears or crystals, they were made of the sky, the earth, and the endlessly repeating patterns of the natural world. For early humans, time wasn't an abstract measurement. It was the rhythm of life itself, written into the cycles of light and dark, growth and decay, heat and cold. The most obvious of these first clocks was the rising and setting of the sun. This daily cycle was universal, constant, and impossible to ignore. For early hunter-gatherers, the sun's journey marked the boundary between activity and rest, danger and safety. Daytime meant hunting, foraging, building, and traveling. Nighttime meant firelight, shelter, and caution against predators. The sun's arc across the sky didn't just tell people when to act, it also served as the first predictable pattern they could rely on, a certainty in an uncertain world. But human beings quickly learned that there were larger, slower cycles too. The waxing and waning of the moon provided another natural marker. Its phases repeated roughly every 29.5 days, offering a way to divide the year into months. Even without written records, people could watch the moon's changing face and know how far they were from the last full moon or how close they were to the next. In many early societies, the moon's phases became an essential guide for ritual, travel, and agriculture. Then there were the seasons, the grand clock of the earth itself. Early humans noticed that certain plants grew only at specific times of the year, that animals migrated or bred according to predictable cycles, and that weather patterns followed a repeating rhythm. The movement of the sun along the horizon at sunrise or sunset shifted gradually over months, marking the passing of seasons. Winter's chill would give way to spring's renewal, summer's abundance, and autumn's harvest, before the cycle began again. These annual patterns were not just background scenery, they were the framework for survival. People also learned to read subtler signs. The length of shadows changed not only over the course of a day but also from season to season. The appearance of certain stars or constellations in the night sky signaled the time for planting or harvesting. For example, the rising of the star Sirius before dawn marked the start of the Nile's flooding in ancient Egypt, a life-giving event that determined the agricultural calendar. The stars themselves became part of humanity's timekeeping system, offering markers that repeated with precision year after year. Water and tides added yet another layer to nature's timekeeping. Coastal peoples learned to read the cycle of tides, caused by the gravitational pull of the moon, as a reliable, repeating pattern. Tides influenced fishing, travel, and even religious ceremonies. Just as with the sun and moon, the sea offered its own form of a clock, one that rose and fell with unwavering regularity. For early humans, these natural cycles were more than just environmental facts. They became deeply embedded in culture, myth, and identity. Many early myths personified the sun and moon as deities, and the cycles of day, month, and year as the movements of divine beings. The predictable repetition of these cycles gave a sense of order to the cosmos and to human life. People could predict the return of certain events, when the rains would come, when herds would migrate, when certain foods would be available, simply by watching the sky and land. This natural sense of time also shaped language. Words for day, month, and year in many ancient languages are rooted in the names of celestial bodies or natural phenomena. In a very real sense, early humans didn't separate time from nature, the two were one and the same. The beauty of these first clocks was that they needed no human construction. They were universal and free, available to anyone with eyes to see and memory to recall patterns. They were also the seeds of scientific thinking. Watching the sky and noting the seasons was, in essence, the first form of observation-based measurement. Over time, these observations became more formal and precise. Stone monuments like Stonehenge in England or the ancient observatories of the Maya were aligned with solar and lunar events. These were not primitive guesses, they were highly accurate alignments that required generations of careful observation. By locking structures to the patterns of the sun, moon, and stars, these early civilizations created the first permanent records of nature's clockwork. In this way, the rising sun, the changing moon, the turning seasons, the stars above, and the tides below all served as humanity's first, and for millennia, only, methods of keeping time. These were the rhythms that bound human life to the earth and the cosmos, setting the pace of survival, culture, and even spirituality. And from these natural patterns, humanity would take the next step, turning nature's rhythms into human-made systems of timekeeping, the beginnings of calendars and, eventually, mechanical clocks. Once humans began settling in one place and cultivating crops, their relationship with time changed dramatically. No longer could they rely solely on a daily awareness of the sun's position or the passing of seasons through observation alone. They needed a systematic way to plan ahead. Agriculture demanded precision. Seeds had to be planted at the right moment. Harvests had to be timed before the rains or frosts. A missed cue could mean famine. And so, humanity's need to organize life in sync with nature gave birth to one of the most revolutionary inventions in history: the calendar. The earliest calendars were born from the same cycles that guided humanity's first clocks: the sun, the moon, and the stars. The challenge was that these cycles didn't line up neatly. A lunar month lasts about 29.5 days, meaning 12 lunar months add up to roughly 354 days, about 11 days short of the solar year. Over time, this difference causes the lunar calendar to drift out of sync with the seasons. Early timekeepers had to find ways to reconcile these mismatches, and each culture came up with its own solution. In Mesopotamia, one of the cradles of civilization, the Sumerians developed a lunar-solar calendar around 3000 BCE. It tracked months by the moon but inserted extra months periodically to keep the year aligned with the agricultural cycle. This practice, called intercalation, required astronomical observation and careful record-keeping, tasks often managed by priestly scholars. The Babylonians refined this system, giving rise to a calendar that influenced both Hebrew and Greek timekeeping traditions. The ancient Egyptians, dependent on the flooding of the Nile, created a purely solar calendar of 365 days, divided into 12 months of 30 days each, plus 5 extra days at the end of the year. Their year was closely tied to the heliacal rising of Sirius, which coincided with the Nile's inundation, a vital signal for planting crops. Because their year was slightly shorter than the true solar year of about 365.24 days, the Egyptian calendar slowly drifted relative to the seasons, but for religious and agricultural purposes, it worked well enough for centuries. In Mesoamerica, the Maya achieved astonishing accuracy with their timekeeping. They devised two main calendars: the 260-day Tzolkin, used for religious and ceremonial purposes, and the 365-day Hab, tied to the solar year. These two interlocked in a 52-year cycle known as the calendar round, a period of immense cultural significance. The Maya also tracked longer spans of time with the long count calendar, allowing them to record historical events over thousands of years. Their astronomical observations, especially of Venus and eclipses, rivaled those of the Old World in precision. China's calendar traditions were similarly complex, blending lunar and solar measurements. The traditional Chinese calendar is lunar-solar, with months beginning on the new moon and leap months added to keep in step with the solar year. This calendar wasn't just agricultural, it regulated festivals, state rituals, and even political legitimacy, as emperors were expected to announce the new year and its cycles correctly. An error in timekeeping could be interpreted as a sign of losing the mandate of heaven. Calendars also emerged in ancient India, where astronomical knowledge was tied to religious and agricultural life. Indian calendars, such as the Hindu Panchang, are lunar-solar and incorporate complex calculations involving the positions of the sun, moon, and planets. These systems determined not only planting times but also auspicious dates for marriages, journeys, and religious ceremonies. The Roman calendar, which many modern calendars descend from, began as a lunar system but underwent major reforms. Early Roman months alternated between 29 and 31 days, with occasional extra months added haphazardly, often manipulated for political purposes. By the 1st century BCE, the system was so misaligned with the seasons that Julius Caesar, advised by the Alexandrian astronomer Sosigenes, introduced the Julian calendar. This reform established a solar year of 365 days with a leap year every 4 years, simple, stable, and practical for the empire's administrative needs. Over centuries, even the Julian calendar drifted by about 1 day every 128 years, leading to a mismatch between calendar dates and astronomical events like the spring equinox. This eventually prompted Pope Gregory XIII to introduce the Gregorian calendar in 1582. The reform adjusted leap year rules. Century years would only be leap years if divisible by 400, and skipped several days to bring the calendar back into alignment with the equinox. This Gregorian system, or variations of it, is now used by most of the world. What's striking is that calendars were never just about marking days, they were tools of power and culture. Rulers used calendars to unify their territories, coordinate armies, collect taxes, and schedule festivals that reinforced social cohesion. Religious authorities used them to fix the dates of holy days, turning the measurement of time into a sacred duty. Merchants relied on them to set markets, fairs, and trade expeditions. In every civilization, whoever controlled the calendar, in effect, controlled the rhythm of life. The invention of calendars represented humanity's first great step toward mastering time, not in the sense of stopping or altering it, but in bringing its cycles under conscious control. From then on, people were no longer passive observers of nature's rhythms. They were active participants, shaping their lives around a human-made structure of time. And with this structure in place, the door was open for the next leap, measuring not just days and months, but the hours and minutes that make up each day, leading to the birth of mechanical timekeeping. In the early Middle Ages, most people still experienced time as a broad, natural rhythm. Sunrise for starting the day, sunset for ending it, church bells for marking the canonical hours of prayer. Days were divided loosely into morning, afternoon, and night, and precision beyond that was rare outside of certain religious or scholarly contexts. But all of that began to change with the arrival of mechanical timekeeping, a technological shift that would quietly, but profoundly, reshape human life. Before mechanical clocks, the most advanced timekeeping tools in Europe and the Islamic world were water clocks, clepsydras, and sundials. Water clocks, which measured time by the steady flow of liquid from one container to another, could work both day and night but required constant maintenance and calibration. Sundials worked beautifully under sunlight but were useless on cloudy days or after sunset. These devices were practical for monasteries, courts, and marketplaces, but they couldn't give the unerring, continuous tracking that mechanical systems would later provide. The earliest mechanical clocks began appearing in European monasteries in the late 13th century, driven not by commerce but by religion. Monastic life was rigidly structured around the liturgy of the hours, which divided the day into fixed periods for prayer, psalms, and work. The ringing of bells announced these moments, ensuring that the entire community moved in harmony. Early mechanical clocks, powered by falling weights and regulated by virgin foliot escapements, allowed these bells to ring automatically at precisely the right times, even in the dead of night. The shift was subtle at first. Monks now had a device that could wake them for matins in the middle of the night without relying on human watchfulness. But over time, the implications spread far beyond cloister walls. By the 14th century, clock towers began rising in European towns and cities. These monumental public clocks did more than tell the hour. They projected civic pride, technological prowess, and a new sense of collective time. Townspeople could now coordinate markets, meetings, and festivals with unprecedented accuracy. Time began to take on a shared, standardized quality that transcended the purely local experience of daylight and weather. Mechanical clocks also brought about a subtle but profound shift in how people thought about their days. Time was no longer an elastic, natural flow but a series of uniform, measurable units. A workday could now be divided into specific hours rather than vague stretches of daylight. For merchants, craftsmen, and guilds, this meant more precise coordination of labor and trade. For the first time, it became possible to schedule activities to the quarter hour instead of sometime in the afternoon. The precision of mechanical clocks also began influencing religious life outside monasteries. Church services in towns could start at exact times, making it easier for large congregations to gather. Religious processions and feasts could be synchronized more tightly, increasing their spectacle and orderliness. In some cases, the clock became a symbol of divine order itself, its steady ticking a reflection of the universe's God-given regularity. But this new time discipline had consequences. While in agricultural life work had been shaped by the sun and the seasons, starting earlier in summer, later in winter, urban life under the clock began imposing the same schedule year-round. Over centuries, this would help create the regimented work patterns that eventually fueled industrial society. Time, once a flexible partner to human needs, was becoming a master to be obeyed. Interestingly, mechanical timekeeping also advanced in the Islamic world, China, and elsewhere, often blending artistry with engineering. The great inventor Al-Jazari, in the 13th century, built elaborate water-powered and mechanical clocks that not only kept time but displayed astronomical data and even featured automated figurines. In China, clock-making traditions stretched back centuries, with engineers like Song designing towering astronomical clocks in the 11th century that combined celestial observation with mechanical precision. In medieval Europe, however, the spread of the weight-driven mechanical clock was unique in how it penetrated public life. By the late Middle Ages, virtually every major town had a clock tower, and the hourly chime became an inescapable feature of daily experience. Bells didn't just announce the hour, they announced the authority of the town, the church, or the ruling power that had built the clock. Time itself had become a public resource, a kind of shared infrastructure. By the Renaissance, clockmaking had become a high craft, with innovations like the spring-driven mechanism allowing smaller, portable clocks to be made. These weren't just functional, they were symbols of wealth and sophistication. Time was now something that could be carried on your person, making the individual, not just the community, subject to its measurement. The arrival of mechanical timekeeping in the Middle Ages was more than a technological milestone. It was a cultural transformation. It introduced the idea that time could be divided, controlled, and standardized, setting the stage for the rise of punctuality as a social virtue. It changed the rhythm of work, the coordination of worship, and the heartbeat of the city. It marked the moment when humans began not just to follow time, but to enforce it, and that shift would echo through the coming centuries, paving the way for railroads, factories, and the synchronized global world we live in today. By the dawn of the 19th century, mechanical timekeeping had already transformed cities, commerce, and culture. Local communities could measure hours with far greater accuracy than in previous centuries. Yet there was still one enormous problem: everyone was keeping their own time. Each town or city set its clocks according to the sun's position directly overhead at noon. This local solar time worked fine in the days when most people lived their entire lives within a short travel radius. But with the coming of the Industrial Revolution, and especially the rise of the railroads, this patchwork of local times became chaos. Imagine trying to run a train schedule when every city along the route is on a slightly different time. A train leaving Bristol might depart at 10 o'clock Bristol time but arrive in London at 12:15 London time, which could be a difference of only 2 hours in travel but also several minutes in clock time depending on longitude. For passengers, freight companies, and railroad operators, this mismatch was a nightmare. Trains could collide if timetables were misunderstood, and coordinating long-distance journeys was nearly impossible without a common standard. Railroads were the first major force to demand synchronized time on a wide scale. In Britain, the Great Western Railway led the charge in the 1840s, adopting London time, set to Greenwich, for its schedules. Soon, other railways followed suit, and by the 1850s, railway time based on Greenwich Mean Time, GMT, had spread across the country, even before it was officially adopted by the government. The shift wasn't entirely smooth. Some towns resisted, proudly keeping their local time on public clocks, but practicality won out. For the first time, people were living on a shared national clock. In North America, the problem was far greater. The United States and Canada spanned vast distances, with dozens of local times differing by minutes or even hours. Before synchronization, American railroads used over 70 different local times to run their networks. In 1883, the railroads decided to end the confusion by adopting a standardized system of time zones. On November 18th of that year, known as the Day of Two Noons, railway stations across the continent reset their clocks to match one of 4 standard zones. For many towns, noon suddenly came either a little earlier or a little later than it had the day before, marking a symbolic break from purely local timekeeping. The need for global synchronization didn't stop at railroads. The invention of the telegraph in the mid-19th century suddenly allowed messages to travel faster than people for the first time in history. This made time differences across regions even more obvious, and more inconvenient. Telegraph companies, shipping lines, and eventually international commerce all required some way to agree on a universal standard. Without it, even something as simple as confirming a meeting time across continents could be a logistical puzzle. This growing demand for precision and unity led to the International Meridian Conference in Washington, D.C., in 1884. Delegates from 26 nations agreed to adopt the Greenwich Meridian in London as the world's prime meridian, longitude 0°, and to base the global time standard on Greenwich Mean Time. The Earth was divided into 24 time zones, each roughly 15 degrees of longitude apart, corresponding to 1 hour's difference in solar time. This was a monumental step in organizing the world into a coherent, shared temporal framework. For the first time in human history, it was possible to coordinate activities across oceans with confidence. Shipping schedules became more reliable. Telegraph messages could reference a single agreed-upon time, avoiding confusion. Scientists could synchronize astronomical observations from distant points on the globe. And as the 20th century approached, technologies like the telephone and, later, radio broadcasting would make global synchronization not just useful but essential. The cultural impact was equally significant. Local communities were no longer sovereign over their own clocks. Time was now dictated from a central authority, whether that authority was the national capital or an international standard. This fostered a sense of connection between distant places. London and New York were no longer just geographically linked but temporally linked as well. At the same time, it was a subtle surrender of local identity to the demands of industry, commerce, and technology. It's worth noting that the introduction of time zones didn't just happen to people, it also shaped the way they thought. The idea that it's 9 o'clock in New York but 2 o'clock in London is now second nature. But it took a mental shift to see time not as an absolute universal or purely local phenomenon but as something that could be systematically divided and assigned across the globe. This mental framework paved the way for the even more precise, global systems that would come later, like Coordinated Universal Time, UTC, and atomic clocks. By the end of the 19th century, the world had, for the first time, a shared temporal infrastructure. The sun still rose and set as it always had, but human beings had imposed a grid of hours and minutes over the entire planet, a web of synchronized clocks that ticked in unison from one side of the Earth to the other. This system would prove to be the backbone of modern transportation, communication, and eventually, the digital networks that define the 21st century. By the mid-20th century, humanity's mastery of time had already reached an astonishing level of synchronization. The global system of time zones, coordinated by observatories and telegraph signals, kept the world running in step. But there was still a problem. The traditional standard for measuring time, based on Earth's rotation, wasn't perfectly reliable. Our planet wobbles slightly on its axis, its rotation slows minutely over long periods, and tidal forces from the moon cause tiny but measurable variations. For most of history, these fluctuations didn't matter. But in an age of space exploration, global communication, and high-speed computing, even the tiniest irregularities could cause big problems. The solution came not from astronomy, but from the heart of the atom. Atomic timekeeping works on a radically different principle than earlier methods. Instead of relying on celestial motions, it measures time by the incredibly consistent vibrations of atoms. Specifically, modern atomic clocks most often use the element cesium, cesium-133, to be exact. Atoms of cesium, when exposed to the right energy, resonate between two specific energy states at an extraordinarily stable frequency. That frequency, 9,192,631,770 oscillations per second, was chosen to define the length of 1 second in the International System of Units, SI. This is not an arbitrary choice, it is a direct reflection of nature's fundamental consistency. The leap in precision that atomic clocks provided was staggering. While the best pendulum clocks in the 18th century might drift by a second every few days, and quartz crystal clocks by a second every few years, the most advanced atomic clocks today can keep time so accurately that they would lose or gain less than a second over hundreds of millions of years. This near perfection gave scientists and engineers a time standard that was not tied to the irregularities of the Earth's rotation but to the unchanging behavior of matter itself. This precision changed the game for science and technology. One of the most transformative applications has been the Global Positioning System, GPS. GPS satellites each carry highly accurate atomic clocks, and they broadcast their exact time to receivers on Earth. By comparing the time signals from multiple satellites, a GPS receiver can calculate your position to within a few meters, or even centimeters with advanced systems. Without atomic time, GPS would drift rapidly out of accuracy, making navigation unreliable for everything from smartphones to airplanes to ships. But GPS is just one example. Atomic clocks are also essential for deep space communication, allowing space agencies to track spacecraft traveling millions of kilometers from Earth with pinpoint accuracy. They are used in particle physics experiments, where sub-nanosecond timing can make the difference between detecting a rare event and missing it entirely. Telecommunications networks rely on atomic time to synchronize data packets traveling around the world, ensuring that voice calls, video streams, and financial transactions happen in the correct sequence. Perhaps even more profoundly, atomic timekeeping forced a refinement of our global time standard. Since the 1960s, the second has been officially defined by the cesium frequency, but the world's clocks still need to stay in sync with the rotation of the Earth for practical purposes like determining sunrise and sunset. This led to the invention of leap seconds, occasional adjustments added to Coordinated Universal Time, UTC, to keep it aligned with mean solar time. Leap seconds are rare, but they're a reminder that our human experience of time is still tied to the motions of our planet, even as our measurements have moved into the atomic realm. The pursuit of even greater accuracy hasn't stopped. Scientists are now developing optical lattice clocks, which use atoms like strontium or ytterbium and operate at frequencies thousands of times higher than cesium. These could eventually measure time with such precision that they could detect minuscule changes in gravity, enabling applications from geophysics to testing Einstein's theories in new ways. Atomic time has done more than give us a better clock, it has redefined what we mean by precision itself. For the first time, our measure of time is not dependent on the behavior of our planet or the reliability of human-made devices, but on the unchanging properties of the universe's building blocks. It is a standard written not in the turning of the Earth or the ticking of gears, but in the language of physics itself. And yet, even as our ability to measure time has reached such dizzying accuracy, the question of what time is, whether it is a thing, a process, or an illusion, remains as mysterious as ever. Still, atomic time has given us the most reliable ruler we have ever had to measure that mystery, and with it, we have built technologies that connect the world, explore the stars, and peer into the deepest truths of nature. In the late 17th century, when Isaac Newton laid out his Philosophiae Naturalis Principia Mathematica, he didn't just present the laws of motion and gravitation, he also gave the world a vision of time that would dominate scientific thinking for over 2 centuries. For Newton, time was absolute, a vast, invisible river flowing steadily and uniformly, independent of the events within it or the observers experiencing it. In Newton's framework, this absolute time was like the stage on which the universe's drama unfolded. The actors, the planets, the stars, the falling apples, moved according to the laws of motion, but the stage itself remained unchanged. Whether you were in London or on the moon, time, in Newton's view, flowed at the same rate. It ticked away relentlessly, indifferent to location, speed, or gravity. It was true and mathematical time, distinct from the imperfect measurements humans might make with clocks. Why did this view seem so convincing? In Newton's day, it matched common experience and the best available science. People knew that clocks could be synchronized and that events could be ordered in a universal before and after. The motions of the planets and pendulums could be described with equations that assumed a single, unchanging timeline. Whether you were tracking the swing of a pendulum in Paris or the fall of a cannonball in Beijing, the same formulas worked, suggesting that the same time flowed for everyone, everywhere. Absolute time also made sense philosophically in Newton's era. It fit neatly with the idea of a clockwork universe, set in motion by a divine creator and running on perfect, predictable laws. In this worldview, absolute time was part of the divine architecture, an eternal, unalterable background against which God had placed the machinery of the cosmos. The very idea of God's time seemed to align with the notion that there was one true, universal clock. Newton himself contrasted absolute time with relative time, the practical, human-made timescales we use in daily life. Relative time could be measured by clocks, calendars, or the motion of celestial bodies, but it was, in his words, a sensible and external measure of duration rather than the real thing. Absolute time, by contrast, was an invisible, pure duration, flowing equably without relation to anything external. You couldn't see or touch it, but it was there, underpinning the universe like an invisible metronome. For centuries, this idea went unchallenged. The success of Newtonian mechanics in explaining everything from planetary orbits to the motion of tides reinforced the belief that time was a constant, universal backdrop. Even great thinkers like Immanuel Kant, though more philosophically cautious, treated time as an a priori condition of experience, a fundamental feature of reality without which the world would be unintelligible. In practical terms, Newton's absolute time was a godsend for science and engineering. It allowed astronomers to predict eclipses decades in advance, navigators to chart their positions across oceans, and engineers to design machines with predictable cycles. The uniformity of time was taken as a given, the same way the solidity of matter or the reliability of gravity was. And yet, cracks in the concept began to appear as the 19th century drew to a close. The rise of electromagnetism, the discovery of the finite speed of light, and increasingly precise measurements began to hint that the universe might not respect Newton's unchanging temporal stage. Still, before Einstein's revolution, the assumption remained: if two events happen a second apart in one place, they happen a second apart everywhere, for everyone. For all its eventual limitations, Newton's concept of absolute time was an intellectual triumph for its age. It provided a coherent, universal framework that allowed the scientific revolution to flourish. Without it, the mathematics of classical mechanics, and much of early modern science, would have been impossible. Even today, in many everyday situations, Newton's model is good enough to describe reality. You don't need relativity to calculate how long it takes your coffee to cool or your car to travel a mile. But as the 20th century dawned, a new understanding of time emerged, one that would shatter the notion of its absolute flow and replace it with something far stranger: the idea that time itself could stretch, shrink, and bend depending on your perspective. The era of Newton's universal river was coming to an end. When Albert Einstein published his theory of special relativity in 1905, he wasn't just rewriting the laws of motion, he was striking at the very heart of Newton's absolute time. The idea that time flowed uniformly for everyone, everywhere, was so deeply ingrained in both science and common sense that most people couldn't imagine it being otherwise. Yet Einstein's equations said something astonishing: the passage of time depends on how fast you're moving and where you are in the universe. Time, in other words, is not absolute, it's relative. Special relativity emerged from a puzzle in physics. In the late 19th century, James Clerk Maxwell's equations had shown that the speed of light in a vacuum was constant, about 299,792 kilometers per second, no matter how fast you moved relative to the source. But that made no sense in Newton's framework. If you threw a ball from a moving train, its speed would be the train's speed plus the throw's speed. Why wouldn't light behave the same way? Einstein's breakthrough was to realize that the laws of physics, and the speed of light, must be the same for all observers, regardless of their motion. This meant that space and time couldn't be fixed backdrops. Instead, they were flexible, interwoven aspects of reality. To preserve the constant speed of light, space could stretch and time could slow down depending on an observer's frame of reference. This led to the concept of time dilation. Imagine two identical clocks. One stays on Earth, the other travels on a spaceship moving close to the speed of light. According to special relativity, the moving clock will tick more slowly compared to the one on Earth. When the spaceship returns, its clock will show less elapsed time, meaning the traveler has aged less than those who stayed behind. This isn't a trick of perception. It's a genuine difference in the amount of time experienced. Special relativity also introduced the idea of simultaneity being relative. Two events that appear to happen at the same time for one observer may occur at different times for another observer moving at a different velocity. There is no universal now that everyone in the universe shares. Einstein's later theory of general relativity, published in 1915, expanded this concept even further by bringing gravity into the picture. In general relativity, gravity isn't a force pulling objects together but the curvature of space-time caused by mass and energy. Massive objects like planets and stars warp the fabric of space-time, and this curvature affects the passage of time. This means time runs more slowly in stronger gravitational fields, a phenomenon known as gravitational time dilation. If you were to stand near the surface of a neutron star, where gravity is immensely stronger than on Earth, your clock would tick far more slowly relative to someone farther away from the star. Even on Earth, this effect is measurable. Clocks at sea level run slightly slower than clocks at higher altitudes because they are deeper in Earth's gravitational well. The implications of time dilation are profound and have been confirmed by countless experiments. In 1971, the Hayfel-Keating experiment flew atomic clocks on commercial airliners around the world and compared them to stationary clocks on the ground. The results matched Einstein's predictions. The airborne clocks experienced both special relativistic time dilation, due to their speed, and general relativistic time dilation, due to changes in gravitational potential. Today, these effects aren't just theoretical curiosities, They're essential to modern technology. The GPS satellites orbiting Earth experience less gravity than clocks on the surface and also move at high speeds. Both effects change the rate at which their onboard atomic clocks tick. Engineers must correct for these relativistic differences. Without such adjustments, GPS positions would drift by kilometers each day. Perhaps the most mind-bending implication of Einstein's work is that there is no single, universal river of time. Instead, every observer has their own proper time, the time they personally experience, shaped by their speed and position in a gravitational field. The concept of an objective, shared timeline for the entire universe simply doesn't exist in the relativistic framework. This reimagining of time shook the foundations of physics and philosophy alike. It forced us to abandon the comfort of Newton's eternal, unchanging clock and accept a universe in which time itself can stretch, shrink, and warp depending on your journey through space-time. And if speed and gravity can bend time, then near the most extreme environments, like black holes, those effects might become so extreme that time nearly stops altogether. When Einstein unveiled general relativity in 1915, he didn't just give us a new theory of gravity, he gave us a radical reimagining of the stage on which the universe plays out. Gravity, in his view, wasn't a mysterious force reaching across empty space, as Newton had described. Instead, mass and energy physically bend the fabric of space-time, and objects, including light, follow the curves and contours of that geometry. This bending of space-time has a strange consequence. It doesn't just affect the paths of planets or the trajectory of falling apples, it changes the very rate at which time passes. The deeper you are in a gravitational field, the more slowly time moves relative to regions with weaker gravity. This phenomenon, gravitational time dilation, is a direct result of space-time curvature. The more massive an object, the more it warps space-time, and the stronger the slowing effect. To visualize it, imagine space-time as a flexible sheet. Place a bowling ball on the sheet, it sinks down, creating a dip. That dip represents the curvature caused by a massive body like Earth. Now imagine a tiny stopwatch resting at the bottom of that dip. It will tick more slowly compared to an identical stopwatch far away on the flat, uncurved part of the sheet. This isn't because the stopwatch is broken, it's because time itself is running differently in that location. Here on Earth, the effect is small but measurable. Highly accurate atomic clocks placed at the top of a tall building run slightly faster than identical clocks at ground level because they're farther from the planet's center of gravity and thus in a weaker gravitational field. In 2010, scientists at the National Institute of Standards and Technology, NIST, demonstrated that even a height difference of just 33 centimeters is enough for modern atomic clocks to detect a change in the rate of time. That means your head is technically aging faster than your feet right now. In stronger gravitational fields, the effect becomes more dramatic. Take a neutron star, a city-sized remnant of a collapsed star with a mass greater than the Sun's. Its gravity is so intense that time near its surface runs significantly slower compared to far away. If you could hover just above a neutron star for what you experience as 1 hour, someone observing from a safe distance might see that many hours, or even days, had passed. But the most extreme example occurs near a black hole. In these cosmic abysses, gravity is so powerful that it creates an event horizon, a boundary beyond which nothing, not even light, can escape. As you approach the event horizon, gravitational time dilation intensifies. From the perspective of a distant observer, your clock would appear to tick slower and slower until, right at the horizon, it would seem to stop altogether. To you, on the other hand, time would feel normal. You'd notice nothing unusual about your watch or heartbeat, but looking out, you'd see the universe beyond speeding up at a dizzying rate. This extreme slowing of time near a black hole isn't just theoretical, it has been depicted, with scientific consultation, in films like Interstellar, where astronauts visiting a planet near a supermassive black hole experience hours while years pass for those farther away. While Hollywood took some liberties, the underlying physics is sound. The gravitational field of such a massive object can stretch time to almost unimaginable degrees. These effects are not just curiosities for science fiction, they have practical consequences even in everyday technology. As mentioned before, GPS satellites must account for both special relativistic time dilation, due to their speed, and gravitational time dilation, due to being higher in Earth's gravitational well. Without correcting for both, GPS would fail within hours. Einstein's insight that gravity and time are intertwined changed our understanding of the cosmos. Massive objects don't just bend the paths of moving bodies, they bend the flow of time itself. This means that the universe is not ticking at the same rate everywhere. It's a patchwork of different temporal experiences, sewn together by the fabric of space-time. And as we push further into exploring extreme environments, like the space near black holes or the early universe, understanding how gravity shapes time will be essential. In those places, the slowing, and perhaps even the end, of time as we know it becomes not just a possibility, but an inevitability. If Einstein's theories showed us that time is flexible, able to stretch, shrink, and bend, there's still one stubborn feature of time that no experiment or observation has ever contradicted: it moves forward. We remember the past, but not the future. A cup can fall and shatter, but shattered pieces never spontaneously leap together to form a cup. You can watch cream swirl into coffee, but you'll never see it swirl back out again. This persistent one-way flow is called the arrow of time, and the key to understanding it lies in a concept from thermodynamics: entropy. Entropy is, in simple terms, a measure of disorder. The more mixed up and random a system is, the higher its entropy. A neatly stacked pile of books has low entropy. Books scattered haphazardly across the floor have high entropy. And here's the crucial part. The second law of thermodynamics says that in an isolated system, entropy tends to increase over time. Systems naturally evolve from order to disorder, not the other way around. This tendency is statistical in nature. It's not that lower entropy states are impossible, just that they're incredibly unlikely. Imagine all the air molecules in your room suddenly gathering in one corner. The laws of physics technically allow it, but the odds are so astronomically small that it will never happen in your lifetime, or in the lifetime of the universe. Overwhelming probability ensures that things move from order to disorder. That's why the arrow of time is tied so deeply to entropy. When you see cream mixing into coffee, countless microscopic collisions between molecules disperse the cream's particles throughout the liquid. There are vastly more ways for those particles to be evenly spread than to be separated. So once mixed, they stay mixed. You never see them spontaneously reseparate, not because the laws of physics forbid it, but because the odds are so small they might as well be zero. What's fascinating is that the fundamental laws of physics, the equations governing gravity, electromagnetism, and even quantum mechanics, don't actually prefer one time direction over another. They're time-symmetric, meaning if you reverse the motion of every particle, the equations would still work perfectly. A billiard ball rolling forward behaves exactly the same, in principle, as a billiard ball rolling backward, at least in the math. So why, then, do we perceive a clear forward march of time? The answer lies in the initial conditions of the universe. For reasons we still don't fully understand, the universe began in a state of incredibly low entropy, an orderly, smooth arrangement of matter and energy. Since then, entropy has been increasing relentlessly, and that increase defines the direction of time. The past is the direction of lower entropy. The future is the direction of higher entropy. This is more than just a scientific curiosity. It's tied to the very structure of memory and consciousness. We remember the past because it was a lower entropy state, and the information about it is encoded in the present in ways that the future isn't. For example, a footprint in wet sand records where a person has walked, but there are no footprints from the future leading backward in time. Our brains themselves are physical systems that rely on thermodynamic processes, so the arrow of time is baked into how we store and recall events. Entropy also shapes the fate of the universe. If the second law holds indefinitely, then the cosmos will eventually reach a state of maximum entropy, a condition sometimes called heat death. In that far-off future, all usable energy will be evenly spread out, all temperature differences erased, and no more work will be possible. In such a universe, time might lose its meaning, because there would be no change, no processes, no before or after, only an eternal, featureless sameness. The arrow of time, then, is a bridge between the microscopic reversibility of physics and the macroscopic irreversibility of life as we experience it. It's why eggs break but don't break, why smoke disperses but doesn't gather back, why you grow older but never younger. And it's a reminder that our forward march is not a fundamental law of nature written into every particle, but rather the outcome of a cosmic story that began in a state of extraordinary order, and has been running downhill ever since. If you were to sit down with the equations that govern the fundamental forces of nature, Newton's laws, Maxwell's equations for electromagnetism, Schrödinger's equation for quantum mechanics, you'd notice something peculiar. They don't care which way time runs. If you replace t with t in those equations, the math still works perfectly. A movie of two planets orbiting each other could be played backward, and the underlying gravitational equations wouldn't know the difference. In the microscopic world of particles and forces, time symmetry seems to be the rule. And yet, when we look at the everyday world, the story is completely different. A glass falls, shatters, and scatters pieces across the floor, but play that in reverse, and it looks absurd. We never see shards leap together to form an intact glass. Your coffee cools down on the table but never warms itself up. People grow older, not younger. This disconnect, between reversible laws on paper and irreversible processes in reality, is one of the deepest puzzles in physics. So where does the asymmetry come from? The key lies in the second law of thermodynamics and the role of probability in physical systems. At the microscopic level, the movement of particles is indeed reversible. But in practice, physical systems involve enormous numbers of particles, on the order of 10^23, in a glass of water, and the vast majority of possible configurations correspond to higher entropy states. When you drop ice cubes into warm tea, the molecules of heat energy disperse from the tea into the ice, melting it. The reverse process, heat spontaneously concentrating to refreeze the water into ice, would require all those particles to coincidentally move in just the right way, something so statistically improbable that it simply doesn't happen in nature. The arrow of time, which we explored in the previous segment, emerges from these statistical realities. But the deeper mystery is why the universe started in such an incredibly low entropy state in the first place. This past hypothesis, as philosophers of physics call it, is the root cause of all macroscopic irreversibility. If the Big Bang had produced a high-entropy, messy universe right from the start, time as we know it, marked by a progression from order to disorder, would never have emerged. There are other, subtler hints in physics that not everything is perfectly time-reversible. In particle physics, for example, certain rare processes involving subatomic particles, like the decay of kaons, violate a principle called CP symmetry, which is linked, through the Kapton theorem, to a tiny preference for one direction in time. But these effects are so minuscule compared to the thermodynamic arrow of time that they don't explain the macroscopic irreversibility we experience daily. This raises profound questions. Is time's apparent one-way flow simply an emergent property of large systems, or is there something deeper in the fabric of the universe that truly breaks time symmetry? Could it be that at the smallest scales, below even the Planck time behaves differently? On the human level, irreversibility defines our entire existence. Our bodies age because biological processes, cellular decay, chemical breakdown, are subject to entropy increase. Our memories are records of lower entropy configurations from the past. Even our sense of cause and effect, this happens because that happened, depends on the fact that effects come after causes, not before. And here's an intriguing thought experiment. If you could somehow reverse all the motions of all the particles in a closed system, literally flip their velocities, you would make the system evolve backward in time. The glass would reassemble, the coffee would heat up, you'd grow younger. But achieving that reversal is so incomprehensibly unlikely in a system with trillions of interacting particles that, for all practical purposes, it's impossible. So the world we live in is one where the microscopic rules are reversible, but the macroscopic outcomes are not. Life moves forward not because the laws of physics demand it, but because the initial conditions of the universe and the statistical weight of disorder make any other direction vanishingly improbable. In a way, this asymmetry is what gives life meaning. Without irreversibility, there would be no history, no growth, no aging, no unfolding of events. Everything would be static in a strange, symmetrical dance, and the idea of before and after would vanish. That's the strange paradox. The very thing that leads to decay, loss, and eventual death is also the thing that makes change, progress, and existence possible at all. If classical physics already made time slippery, stretching, bending, and slowing, quantum mechanics takes that slipperiness and pushes it into a realm that's downright unsettling. In our everyday lives, time feels like an unbroken line, past, present, future. But in the strange world of quantum physics, time doesn't always play. by those rules. In fact, some physicists suspect that time itself might not be a fundamental ingredient of reality at all. In the quantum realm, particles can exist in superpositions, meaning they don't have definite properties until they are measured. An electron can be in multiple places at once, a photon can take multiple paths simultaneously, and a quantum bit in a computer can be both 0 and 1 at the same time. But here's the catch: the standard equations of quantum mechanics, like the Schrödinger equation, are themselves time-symmetric. They don't prefer past or future, much like classical physics. The weirdness emerges when we make a measurement. When a quantum system is observed, the superposition collapses into a definite outcome. This collapse appears to happen in a definite direction. We see results in the present, based on measurements of the past, not the future. But this direction is not something the fundamental equations specify. It's tied to the same entropic arrow of time we discussed before. In other words, quantum measurement seems to inherit the one-way flow of time from the thermodynamic world, not from the underlying quantum rules themselves. Then there's the question of entanglement, where two particles share a single quantum state, no matter how far apart they are. When you measure one, the other's state is instantly determined, even if it's light years away. This spooky action at a distance happens without any obvious flow of time between cause and effect. The correlations between measurements seem to be set outside the normal march of time, as though the particles are part of a timeless whole. Some interpretations of quantum mechanics, like the transactional interpretation, even suggest that particles can send waves both forward and backward in time, meeting in the middle to produce the events we observe. This idea is not mainstream, but it captures a deeper truth. Quantum theory does not forbid influences that, from our point of view, might look like they come from the future as well as the past. But perhaps the most unsettling quantum puzzle about time comes from attempts to unify quantum mechanics with general relativity. In Einstein's theory, time is part of the fabric of space-time, a flexible, dynamic quantity that can be warped by mass and energy. In quantum mechanics, time is treated as something fixed, a stage on which particles play out their probabilistic dramas. This mismatch has led some theorists to suggest that time might emerge from a deeper, timeless reality. In certain approaches to quantum gravity, such as the Wheeler-DeWitt equation, time doesn't even appear in the fundamental equations at all. The universe, at its deepest level, might simply be, without flowing from past to future. In this view, what we experience as time could be a kind of illusion, an emergent property that arises only when we zoom out from the quantum level to the scale of everyday life. This timeless perspective is mind-bending because it means that our most basic intuitions, about change, duration, and sequence, could be nothing more than artifacts of how our brains and senses interact with the universe. From a certain vantage point, all moments, past, present, and future, might coexist in a vast, unchanging quantum structure, and our perception of moving through them would be like flipping through the frames of a cosmic film reel. Yet, even if time isn't fundamental, it's still indispensable in practice. Quantum mechanics uses it in equations, we measure it in experiments, and our lives depend on it. So the real mystery isn't just what is time, but why does a timeless quantum world give rise to a time-bound human experience? If you keep slicing time into smaller and smaller pieces, you eventually reach a point where our current understanding of physics simply breaks down. That point is called Planck time, and it is unimaginably short. One Planck time is about 5.39 times 10 carat minus 44 seconds. To put that in perspective, if 1 second was stretched to the age of the universe, around 13.8 billion years, a single Planck time would be like a fraction of the smallest possible instant you could imagine, so small that it makes a nanosecond look like eternity. The idea of Planck time comes from combining three of nature's most fundamental constants. At the speed of light, c, how fast light, and any causal influence, can travel. At the gravitational constant, g, the strength of gravity. At Planck's constant, bar, the quantum scale constant that sets the size of energy packets. When you combine these constants in a certain way, you get the Planck time. Tundoscopy equals /QRT, /frac, bar g, c to the power of 5. It's the time it would take for light to travel 1 Planck length, about 1.616 times 10 carat, minus 35 meters, the smallest meaningful unit of space we can define using known physics. Why is this number so important? because it marks the limit beyond which our theories stop working. 4 times longer than the Planck time, we can use Einstein's general relativity to describe gravity and spacetime, and we can use quantum mechanics to describe particles and forces. But at or below the Planck scale, the gravitational field itself would have to be treated quantum mechanically, and we don't yet have a complete theory of quantum gravity to do that. Imagine rewinding the universe's history all the way back to the very first moments after the Big Bang. We can trace events back to roughly 1 Planck time after the beginning, but before that, our equations become meaningless. Spacetime may have been so warped and turbulent at such scales that it no longer makes sense to talk about smooth geometry or continuous time at all. In other words, below the Planck time, the concept of time might not even exist in the way we understand it. Some physicists think the Planck time could represent a kind of minimum tick of the cosmic clock. Just as you can't have half a photon of light, maybe you can't have half a Planck time. Reality might be fundamentally discrete at this scale, with time made up of indivisible atoms of duration. If that's true, then the smooth flow of time we perceive could be an illusion caused by these ultra-fast, indivisible moments flashing by, far too small for any experiment to detect directly. Others argue that the Planck time is just a mathematical threshold, not a physical limit. In this view, time could be continuous all the way down, but our current mathematical tools simply fail to describe it once quantum effects of gravity become dominant. Either way, the Planck time is like a curtain across the stage of the universe. On our side of the curtain, physics gives us answers, predictions, and equations. On the other side, beyond that first unimaginably tiny fraction of a second after the Big Bang, lies a realm of speculation, where ideas like quantum foam, string theory, and loop quantum gravity try to guess at what's happening. If someday we can peek beyond that curtain, if we can unify quantum mechanics and general relativity into a single coherent theory, we might discover that our entire concept of time needs to be rewritten. Maybe it will turn out that time is granular, or maybe it emerges from something more fundamental, like the relationships between quantum events. But for now, the Planck time is as far down the cosmic rabbit hole as we can go. If physics tries to describe time as it exists out there in the universe, neuroscience is concerned with time as it exists in here, inside our heads. And here's the fascinating truth. Your brain doesn't have a clock in the way a watch or a smartphone does. There's no little ticking mechanism behind your eyes counting off seconds. Instead, the experience of time is constructed, pieced together from sensory input, memory, and internal rhythms. And because it's constructed, it's often unreliable, elastic, and deeply subjective. We tend to think of seconds, minutes, and hours as fixed quantities, but the brain treats them like estimates. Researchers have identified a few biological systems that work together to give us our sense of timing. Circadian rhythms, governed by the suprachiasmatic nucleus in the hypothalamus, keep track of roughly 24-hour cycles, helping us know when it's day or night. Ultradian and infradian rhythms track shorter or longer cycles, like hormone release patterns or seasonal changes. Milliseconds timing mechanisms, possibly involving the cerebellum and basal ganglia, help us process speech, play music, or catch a ball. But unlike a quartz oscillator in a wristwatch, these systems are influenced by mood, attention, body chemistry, and environment. The result? Our internal clock can stretch or compress time depending on what we're doing and how we're feeling. One of the clearest examples of this comes from moments of fear or danger. People who've been in accidents often report that events seem to happen in slow motion, the screech of tires, the tumble of objects, every detail hyper-detailed. This isn't because time itself slows. It's because the brain goes into high alert mode, processing more information per unit of time. Later, when you recall the memory, the dense amount of stored detail makes the moment seem longer than it really was. On the other hand, when we're bored or waiting, time seems to drag. In these cases, the brain has fewer events to mark the passage of time, so our perception stretches the interval. Ironically, during periods of intense focus, what psychologists call flow, time can vanish entirely. You might sit down to work on a project and look up hours later, shocked at how quickly they passed. The brain's handling of time also explains why certain drugs, like stimulants or psychedelics, can dramatically distort time perception. They alter neurotransmitter activity, changing the rate at which sensory information is processed and stored, leading to experiences of time speeding up, slowing down, or even looping. And here's something counterintuitive. We don't actually perceive the present moment in real time. Neuroscientific experiments suggest the brain works with a short buffer of around a few hundred milliseconds, integrating incoming information into a coherent scene before presenting it to our conscious awareness. In other words, we're always living in the very recent past, not in the true now. Memory plays a huge role too. When you look back on your day, your sense of how long it felt is shaped more by the number of memorable events than by the actual clock time. A day full of novelty, traveling to a new city, meeting new people, feels longer in retrospect than a day spent in repetitive routine. This is sometimes called the holiday paradox. Vacations feel like they fly by while they're happening, but seem long and rich in memory afterward. From an evolutionary perspective, our time perception likely evolved for survival, not precision. Animals, including humans, needed to judge intervals for hunting, avoiding predators, and navigating environments, not for splitting seconds into atomic scale measurements. That's why we're so easily tricked by illusions of time in sports, music, storytelling, and even magic tricks. All of this means that your personal timeline is partly a work of fiction, stitched together by your brain from fragments of perception and memory. The universe's clock may be steady, but the clock in your head is anything but. And because of that, the passage of time in human life is far more flexible, and far more emotional, than the strict ticking of seconds would suggest. When you're a child, summer vacation feels like it lasts forever. By the time you're an adult, entire years can seem to vanish in the blink of an eye. This isn't just nostalgia playing tricks, it's a well-documented psychological phenomenon, and it has several intriguing explanations. The strange part is that it's not the universe speeding up. It's you. One of the most common explanations comes from the proportional theory of time perception. When you're 5 years old, a single year is 20% of your entire life, an enormous chunk of your personal timeline. But at 50 years old, a year is only 2% of your life experience. This shift in proportion means each year feels shorter relative to the total time you've already lived. Even though each year contains the same number of days, your brain compares them to an ever-expanding archive of memories, making new years seem smaller and faster by comparison. Another major factor is the novelty effect. In childhood and adolescence, life is filled with firsts: first school, first friendship, first love, first trip away from home. These novel events demand more attention, and the brain stores more detailed memories of them. As we age, routines take over, and novelty becomes rarer. Days start to blur together because they lack distinct, memorable markers. This is why a year filled with new experiences, travel, career changes, learning a skill, will feel longer than a year spent repeating the same patterns, even if both have the same number of hours. The brain's information processing plays into this as well. Our internal sense of time depends on how many events we encode into memory. The more densely packed an interval is with sensory detail, the longer it feels in hindsight. When you're young, you're constantly learning, absorbing new vocabulary, mastering motor skills, navigating social rules, which packs your early years with rich sensory content. In adulthood, much of daily life is automated. The brain processes familiar experiences with less effort, leaving fewer timestamps in memory. The days may feel long in the moment, but the months and years feel compressed when you look back. Biology may contribute, too. As we get older, metabolic rates slow and the brain's dopamine production decreases. Dopamine is closely linked to how we perceive time intervals. Lower dopamine levels may subtly alter how the brain tracks time, contributing to the sense that it's slipping by more quickly. Emotional state has a huge role as well. Stress, grief, or anxiety can distort time in unpredictable ways, sometimes making it drag, other times making it vanish. But over the long term, a stable, low-novelty lifestyle tends to compress our subjective timeline. This is why retirees often say the years fly by unless they deliberately fill their schedules with new hobbies, challenges, or adventures. There's even evidence from neuroscience that the speed of mental processing might change with age. If your brain is taking in and updating sensory information at a slightly slower rate, your internal frame rate drops. This doesn't mean you perceive things in slow motion. Rather, fewer updates mean fewer mental moments to store, making time feel like it's rushing past. Perhaps the most unsettling part is this: your subjective perception of time affects how you live it. If you feel like you have endless time, you may waste it. If you feel like you're running out, you may use it more wisely, or become paralyzed by the fear of its passing. The good news. The factors that make time feel slower are within reach. Novelty, learning, and emotional intensity stretch our perception of time. That means if you want life to slow down, you don't need to fight the clock, you need to fight monotony. Travel somewhere new, meet new people, learn something challenging, change your routines. The seconds won't actually pass any slower, but your brain will treat them as richer, longer, and more substantial. Asking about the beginning of time is like asking what's north of the North Pole. It pushes language and logic into a place they weren't built to go. Our everyday intuition assumes that everything has a before and an after, but when we're talking about the Big Bang, that mental framework starts to crumble. In the standard cosmological model, the universe began about 13.8 billion years ago in an unimaginably hot, dense state. Space was compressed to a point, and temperatures and energies were so extreme that the familiar laws of physics, as we know them, simply didn't apply. This is where the problem begins. Our best equations, general relativity for gravity, quantum mechanics for the microscopic world, can describe the universe back to a fraction of a second after the Big Bang, specifically, about 1 Planck time, 10⁻⁻43 seconds, but not all the way to zero. At that earliest instant, both quantum effects and gravitational effects were equally important, and we don't yet have a complete theory of quantum gravity to describe them together. So, did time itself start at the Big Bang? According to Einstein's theory of general relativity, time and space are part of the same fabric, space-time. If the Big Bang was the origin of space, then time, being inseparable from space, also came into existence at that moment. In this view, there is no before, because before is a temporal concept, and time didn't exist to allow for a before to happen. Asking what happened before time began is like asking what happened before the universe existed to hold events. It's a question with no physical meaning inside that model. However, not all physicists are satisfied with the idea that the Big Bang was an absolute beginning. Some models suggest that our Big Bang was just one episode in a larger cosmic story. In cyclic or oscillating universe models, the cosmos undergoes endless expansions and contractions, big bangs followed by big crunches, forever. If such a cycle exists, time could extend infinitely into the past, with our Big Bang being just the latest rebirth. Other theories, like the quantum bounce from loop quantum cosmology, propose that the Big Bang was actually a big bounce, a transition from a contracting universe into our current expanding one, caused by quantum effects that prevent spacetime from compressing to a singularity. This would mean there was a before, but it was part of a universe with very different properties from ours. Some speculative proposals even involve eternal inflation. In this idea, our observable universe is just one bubble inside a vast multiverse, with new bubble universes constantly forming from inflating space. In such a scenario, time might stretch infinitely into the past on a cosmic scale, even if our specific bubble has a clear beginning. Then there's the bold suggestion from certain interpretations of quantum mechanics. Time itself might be emergent, not fundamental. According to this view, what we experience as the flow of time could arise from deeper, timeless laws. In this case, the Big Bang might not be the start of time in an absolute sense, just the point at which our particular universe began experiencing time as we know it. And yet, even with these imaginative ideas, we face an enormous observational problem. The further back we look, the more the universe's hot, dense conditions erase the traces of anything before. The cosmic microwave background, the oldest light we can see, is already from nearly 380,000 years after the Big Bang. Everything before that is inferred from mathematics and indirect evidence. So for now, the question of was there a before remains open. Our current best supported theory says no. Time began with the Big Bang. But alternative models suggest maybe, and the universe's history could be far deeper and stranger than we can presently imagine. Until we have a quantum theory of gravity, or some observational clue from the earliest possible moments, we're left with a mystery that's as philosophical as it is scientific. Black holes are nature's most extreme clocks, and the strangest part is that they don't tick the same for everyone. In the warped spacetime around a black hole, time itself becomes flexible, stretching and twisting in ways that defy our everyday intuition. The closer you get to the event horizon, the invisible boundary beyond which nothing, not even light, can escape, the slower time passes relative to someone far away. This effect is a direct prediction of Einstein's general theory of relativity. Gravity doesn't just pull on matter, it warps space-time itself. The stronger the gravitational field, the more this warping affects the passage of time. This phenomenon is called gravitational time dilation. Imagine two identical astronauts with synchronized clocks. One stays far from the black hole, floating in relatively flat space-time. The other, protected by some fantastical technology, drifts near the event horizon. For the astronaut far away, time moves at its usual pace. But for the one near the horizon, each second on their clock corresponds to many seconds, minutes, or even years passing for the distant observer. If the astronaut near the black hole later returns to their friend, they might find that decades have passed for everyone else, while only hours or days passed for them. From the perspective of someone watching an object fall toward a black hole, the view is even more bizarre. As the object approaches the event horizon, its clock appears to slow down, light from it gets increasingly redshifted, and it seems to freeze at the edge, never actually crossing from the outside viewer's standpoint. This is an optical illusion caused by the extreme stretching of space-time and the fact that light from the object takes longer and longer to reach the observer. From the falling object's own point of view, however, it would cross the event horizon in finite time without noticing anything unusual at that exact boundary, until tidal forces and other extreme effects take over deeper inside. If we take this idea to the most extreme example, supermassive black holes, the differences become staggering. A human orbiting close to a supermassive black hole could, in theory, experience only a few hours of subjective time while billions of years pass in the rest of the universe. This isn't science fiction, it's a mathematical consequence of relativity, famously dramatized in Interstellar, where characters orbit a massive black hole and experience severe time dilation compared to their crewmates. Inside the event horizon, the rules change entirely. The singularity at the center of a black hole, if it truly exists as relativity describes, is a point where space-time curvature becomes infinite and our laws of physics break down. In this region, space and time may swap roles in a sense. Instead of being able to choose your spatial path and move forward in time, the forward direction in time inevitably takes you toward the singularity, with no possibility of turning back. From an outside perspective, whatever falls in is lost not only in space but also in time. Black holes also hint at deep connections between gravity, time, and thermodynamics. Stephen Hawking's discovery that black holes emit faint radiation, now called Hawking radiation, suggests they have a temperature and entropy, and that over immense timescales they can evaporate entirely. This raises strange questions. When a black hole evaporates, what happens to the time experienced by anything inside it? Is it cut off entirely, or is there some deeper link to the fabric of the universe? Some speculative theories even suggest that the interior of a black hole could be connected to other regions of spacetime, wormholes or baby universes, where time flows in a completely different way. If true, falling into a black hole might not mean an end to your personal timeline, but a one-way trip to a new one. In the end, black holes are laboratories for the weirdest aspects of time. They show us that time is not absolute, it's malleable, dependent on gravity, and fundamentally tied to the shape of the universe itself. Near a black hole's horizon, time can be slowed almost to a standstill relative to the rest of the cosmos. That means, at least in theory, they are not only destroyers of matter, but also machines for bending the very flow of existence. If the beginning of time is a mystery, the end of time is an even deeper one, because it forces us to confront not only how the universe might die, but whether dying even makes sense for something as abstract as time. Just like its origin, time's ultimate fate depends entirely on the fate of the cosmos itself. And here, cosmologists have several competing scenarios, each as unsettling as it is fascinating. One of the leading contenders is the heat death, also known as the Big Freeze. This idea comes directly from the second law of thermodynamics, which says that in a closed system, entropy, the measure of disorder, can only increase over time. If the universe keeps expanding forever, galaxies will drift apart, stars will burn out, and all matter will eventually decay into a thin soup of elementary particles and radiation. In such a future, there will be no usable energy left to power any processes that could mark the passage of time. Events will become increasingly rare, then non-existent. In a sense, time would lose its meaning, not because it literally stops, but because nothing happens to distinguish one moment from another. The universe would become a featureless, silent void. Then there's the Big Crunch scenario, the mirror image of the Big Bang. If the density of matter in the universe were high enough, gravity could eventually halt the expansion and pull everything back together. Galaxies would collide, temperatures would rise, and eventually, all matter and energy would be compressed back into a state similar to that of the Big Bang. In this model, time could, in principle, end at the singularity, or possibly rebound into a new expansion, creating a cycle of births and deaths for the cosmos. This raises the tantalizing possibility that time might be cyclical rather than linear, with no true beginning or end. A more dramatic idea is the Big Rip. In this scenario, a mysterious force called dark energy, which is already driving the accelerated expansion of the universe, grows stronger over time. If it increases without bound, it could eventually overwhelm all other forces. Galaxies would be torn apart, then solar systems, planets, molecules, and even atoms themselves. At the final moment, space-time would be pulled apart so violently that the concept of before and after might lose all coherence. Time wouldn't just end, it might disintegrate along with the fabric of the universe. There's also the possibility of a vacuum decay event. Our universe might be in a false vacuum state, a temporary and slightly unstable configuration of the quantum fields that underlie reality. If it were to tunnel into a lower energy state, a bubble of this new vacuum could form and expand at nearly the speed of light, rewriting the laws of physics as it went. Inside that bubble, everything we know, including the way time itself behaves, could be erased or radically transformed. The unsettling part is that if such a bubble were heading toward us, we'd never see it coming. One moment, time would be flowing normally. The next, there would be no next at all. But perhaps the most mind-bending idea is that time might transform rather than simply stop. Some theories in quantum gravity and string theory suggest that what we perceive as time could be an emergent property of deeper, timeless laws. If that's true, the end of time might not mean annihilation. It could mean that time dissolves back into whatever underlying reality it came from, much like a wave collapsing into the calm surface of an ocean. In that sense, time's end might feel less like a death and more like waking up from a dream. Of course, there's also the unsettling thought that our universe might not have a single end at all. In a multiverse picture, when our local space-time stops ticking, other universes might still be unfolding their own timelines. The end of our time might be just one chapter in an endless library of cosmic histories. For now, we can't know which, if any, of these futures will come to pass. The heat death could be trillions of years away. The Big Rip might be much sooner, or never. A vacuum decay could happen at any moment without warning. Or time might persist eternally, reshaping itself in ways we can't yet imagine. But perhaps the most important point is this: whatever the ultimate fate of time, it reminds us of its fragility. The flow we take for granted is not guaranteed to last forever. One day, whether slowly or suddenly, the clock may stop, not just for us, but for everything. If the story of time teaches us anything, it's that our experience of it is both precious and precarious. We've journeyed from the cosmic birth of time at the Big Bang, or perhaps before, through its bending around black holes, its slowing and speeding under relativity, its smallest conceivable ticks, and its possible ends in heat death, rip, or collapse. And yet, after all that, one truth rises above the theories. Time is not something we truly understand, yet it is the medium in which our entire lives unfold. This strangeness invites a different way of living. If time is possibly not fundamental, if it could be an emergent property or even an illusion born from change and memory, then our common obsession with controlling it, counting every second, scheduling every moment, feels oddly misplaced. In a universe where space-time bends, where the now is not absolute, and where the past and future may be woven into a single four-dimensional fabric, our everyday clock-watching becomes almost comically provincial. And yet, we can't escape it. For human beings, time isn't just a feature of physics, it's the story of our lives. We mark it in birthdays and anniversaries, in seasons and sunrises, in wrinkles on a loved one's face and the fading sound of a child's laughter. No matter what physics says, we live in the river of time, and it flows one way for us. Accepting time's mystery can make us humble. The universe's clock is vaster than our own. Stars are born and die in spans that make millennia seem like heartbeats. Black holes live longer than the current age of the cosmos. And yet, Here we are, measuring our days in coffee spoons, worrying over late trains, and setting alarms for meetings. Perhaps understanding the cosmic perspective isn't meant to make us anxious about our smallness. It's meant to free us from the illusion that we have to conquer time at all. If time is strange, then maybe the real wisdom is to focus less on its quantity and more on its quality. We can't slow the Earth's orbit or stop entropy's advance, but we can slow our perception, by being present, by paying attention, by noticing life instead of racing past it. A minute spent fully alive, immersed in connection or creativity, can feel larger than an hour of distracted hurry. There's also a liberating possibility in time's mystery. If time is not a rigid, universal flow but something shaped by perspective, then each of us is, in a way, the architect of our own timeline. We can choose what fills it. We can decide what memories to make. And we can live knowing that, whatever the deep nature of time turns out to be, the now is the only place we ever actually meet it. Even the end of time, whether in a cold, lifeless heat death or a cataclysmic big rip, need not be a source of despair. The fact that time will not last forever only sharpens the beauty of its moments now. Just as a sunset is made more breathtaking because we know it will soon fade, the awareness of time's impermanence makes life more vivid, more urgent, more worth living. Perhaps, in the end, the greatest lesson of all the physics, philosophy, and paradox is that time's mystery is not meant to be solved before we can live. It's meant to be lived through while we still have it. We are, for a brief cosmic instant, conscious beings in a universe that has given us the gift of experiencing its unfolding. That's extraordinary. So if time bends, if it can stretch or vanish, if it began with the Big Bang or never began at all, if it will one day end or merely change, none of that alters the fact that this moment, right now, is ours. And the only sane, human thing to do with it is to live it fully, as if it were both eternal and fleeting. Because in a very real sense, it is both. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.